Hi, I'm Brian Clark, and I'm the electrical team lead and president of the Yale Undergraduate Rover Association. Our club's set up in a hierarchical structure that helps to streamline our workflow. I'm the president, and then there are also 4 engineering sub-teams: electrical, mechanical, software, and earth science. Additionally, there are 2 other non-engineering sub-teams: finance and public relations. Each of those sub-teams have their own director, and along with me, we make up the executive board. So with a project of this scale, a lot of money is necessary to complete our goals. And unfortunately, Yale can't provide all of that money for us, so we have to look outside for corporate sponsorships. Yale is, however, generous enough to start us off with $3,000 every year from the School of Engineering and Applied Science. Additionally, the Yale College Dean's Office gave us another $3,000. And on top of that, Yale's Computer Science Department gave us $2,000. As far as corporate sponsorships go, we were very lucky to have ProtoCase give us a $2,000 in-kind sponsorship for this year's competition. Everything on the rover with a blue powder coat was manufactured for free from ProtoCase. They did an excellent job and we're really thankful for it. Additionally, Alcoa gave us $5,000 to help complete our rover. We use that for different parts, some electrical components, as well as shipping.
Hi, my name is Sydney Hershey. I'm the head of PR. My job deals with spreading the word about our club and mission. I organized recruiting meetings and events to help attract new members, and I'm also in charge of social media.
Hi, my name is Patrick Wazinski. I'm a junior mechanical engineering major, and I'm in charge of the mechanical sub-team. The mechanical sub-team this year has been focused on improving our design from last year. Last year's design worked, but it didn't work as well as it could have. So we've been focusing on simplifying and paring down the design to improve it. For our 2015 rover, we decided to custom manufacture our own wheels. This offered a large number of benefits over more traditional wheel designs. One of the biggest benefits was the fact that we could put the motor inside of the wheel to protect it from any sorts of rocks or other obstacles that it might bump into and get damaged. Another benefit was that we could make the wheels as large as we wanted within reason, and could also make the wheels fairly heavy to lower our center of gravity. Another benefit of making our own wheels was that we could custom tune the traction, and so we were able to get much more traction than we were able to in our previous designs. The last benefit would be the ease of attachment of the wheels. Because we were manufacturing our own wheels, we could design the attachment point so that it was a simple set screw connection. For our rover this year, we decided to reuse our previous design for a suspension. So this suspension is a rocker bogie suspension where it has a front rocker and a back bogie. The differential bar coupler is the main differentiating factor between this suspension type and a lot of other rover suspension types. And so this suspension keeps all 6 wheels on the ground at the same time. And so how it does this is when one wheel goes over an obstacle, it will move up and the other wheels will adjust to keep themselves on the ground. So we modeled a lot of our design off of the Curiosity Mars rover. So things such as the in-hub motors and the wheels being cantilevered off of one side of the suspension were directly inspired by NASA's rover. One of the coolest things about the suspension is that it's all completely passive. There's no active elements, there's no springs, there are no shocks. The entirety of the suspension is created by the rover's own weight and by the mechanical linkages. So this is our rover's robotic arm. We're going to be using this for the soil sampling, the equipment servicing, and the astronaut assistance tasks. The arm itself has 4 degrees of freedom. It can rotate at the base, and both the shoulder and elbow joints can rotate, as well as the wrist joint. There's an additional robotic hand that we can add on that has a 5th degree of freedom. The wrist joint is powered by a continuous rotation servo that's geared down. This allows us to have very precise control over the angle of the wrist. It's currently set up for the soil sampling task with our scoop on it. This scoop is going to allow us to dig down 5 centimeters and collect soil samples to be tested by the rover. So we decided to use linear actuators as the primary actuation for our arm this year. as opposed to any sort of motor and belt or gear drive, because the linear actuators give us a large amount of power and also make it much simpler of a design. As you can see, there's only really 2 or 3 moving parts to a linear actuator versus the many more that we had in other designs. For the astronaut assistance and equipment servicing tasks, we have an off-the-shelf robotic gripper that mounts to the front of the wrist. This gripper has been upgraded with high torque servos that will allow it to be very reliable and be able to grip all sorts of objects.
So one of the biggest upgrades between the 2014 and 2015 rovers is the communication system. Last year we used a 5 gigahertz network. This year we upgraded that to a 2.4 gigahertz. And that's going to give us increased range. We've already, through range testing, experienced much better bandwidth range, up to about 1.5 kilometers. So basically the way ours works is we have a ubiquity sector antenna right here. It outputs its signal over 120 degree range, which allows for really good lateral movement of the rover. On the back of this, it has a ubiquity M2 rocket radio that transmits the signal over to the rover. Now the rover uses 2 standard 10 dBi router antennas that do a great job of picking up the signal, and they are connected to another rocket M2. And through that link, our base station computer is able to communicate with the onboard BeagleBone Black. Additionally, we kept the same Logitech C920 webcams on board the rover because they're incredibly reliable, and they saved crucial space because all encoding occurs on the camera. So we did a complete redesign of the rover's electronics enclosure. As you can see, we've got this nice blue enclosure that we designed with proto case. So we have an emergency stop button, a key to start, and then it easily detaches the back plate. And inside you can see the custom shelving we made that divides power distribution, motor control, and communication levels inside the rover. This made it a lot easier to both put the rover together and troubleshoot problems. Last year, we basically had a box of wires. This year we have an orderly shelving system that allows us to control our power distribution more efficiently.
Hi, my name is Adit. I'm a sophomore computer science major here at Yale, and I'm in charge of software for the rover. We have 3 main systems. We have a system that runs on a laptop that's controlled at a ground control. Then we have a small piece of software that runs on the rover that controls the motors. And most of our software is written in Python. We use Python to make our GUIs and to control the motors using the PySerial library.
So if you take a look around, this is our wet lab here in the CEID, where we do a lot of work for the rover. As head of the Earth Science team, a lot of what we're focusing on is more the science capacities of the rover as opposed to the mechanical or software aspects of it.
So on the rover we have a metal scooper to collect the sample, which will be deposited into a sample tray. The first thing that will be analyzed is the humidity of the soil, so that we can look at the water content. Obviously, higher water content is more suitable for life, and so what we use is a small micro humidity meter that connects directly to the BeagleBone unit. That will give us a readout that we can store and analyze on the computer. The next thing that we'll be using is a scale to measure the weight of the samples taken, and this will be used back at the station base So once we've collected a sample, say like this soil here, we can just turn this on and receive a weight reading to the tenth of a gram using this scale. The third component of our soil analysis will be the pH of the soil sample, which we use using HANA Instruments 99121 pH meter. And the great thing about this instrument is that whereas many other pH meters require a solution to measure the pH, this probe can be stuck directly into the soil without having to hydrate with water prior to retrieving the pH. And so here we have a sample of soil, and it's very easy. You simply turn on the HANA meter and then stick the probe into the sample, and it will constantly give a readout, which can be done from the rover out in the field to receive a pH of the soil. And ideally, to support life, we're looking for a fairly neutral pH around 7. There is a range that can go anywhere from 5 to 8.5. But ideally, we'll be looking for soil that is around a pH of 7. And last but not least, we'll be using a portable small microscope to analyze the samples that we have collected. We can bring them back to the station base and get a greater understanding of maybe the components of the soil sample. Fortunately, this microscope also connects to the computers so that we can receive pictures to analyze and maybe compare to other types of soil that are suitable for life.
So overall, we're very excited for this year's University Rover Challenge. We learned a lot in the 2014 University Rover Challenge. It was our first year, so we made a few mistakes, and we had some design flaws that we made sure to take care of this year. I'm going to go task by task and detail what we improved this year based on last year's design. So for terrain traversal, we were having a lot of problems getting over boulders and smaller rocks as well, because our motors kept hitting rocks and preventing forward progress. As Pat Wilczynski mentioned, we put the motors inside the wheels in a design modeled off the Curiosity Mars rover. So this is going to help us navigate obstacles much easier. Additionally, it lowered our center of mass. For equipment servicing, we've totally redesigned the arm. Last year we had a system of belts and pulleys that were really ineffective and ended up breaking halfway through the competition. Once again, as Pat mentioned, we have linear actuators that are going to be really strong. We have a phenomenal gripper that works very well. We're able to turn dials and knobs. So we really look forward to competing in that test. As far as the astronaut assistance task goes, we're also very hopeful that we'll do much better there. We've upgraded our GPS from the SparkFun kit that we used last year to the new Adafruit GPS. This is really accurate, and that's going to help us with tracking things of that nature. In terms of soil sampling, we've got an improved scoop and redesigned sensor suite. We have a humidity sensor as well as a pH sensor this year, and we're confident that we're going to actually be able to retrieve a sample this year.